bubbly, 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 burn, burn, burn. It's chemistry! Woohoo! Let's do some chemistry. Yeah! Hey, everybody. Try that again. Hey, everybody. Welcome back. We're going to be doing a lab today. It's called calorimetry. Coffee cup calorimetry. Where is it? Coffee cup calorimetry. See it over there? Yeah, see it? See it? Okay, cool. Shameless plug for coffee and my favorite TV station. Yay. Shameless, sorry. We are going to be doing some coffee cup calorimetry today. Pretty straightforward lab. We're going to be looking at the amount of energy given off by a chemical reaction. The reaction that we're going to be looking at is the decomposition of hydrogen peroxide. It happens fairly slow to begin with, or by itself, so we're going to catalyze that reaction using some iron 3 nitrate. And so we are going to off into the races. Our purpose behind this, our eventual purpose through calculation, is to calculate the molar enthalpy of the decomposition of hydrogen peroxide. So we're going to have to calculate some moles, and we're going to have to take down lots of numbers and kind of work through this process fairly slow. All right, so let's get going and get started and start looking at some of the stuff we're going to be. All right. What are we going to need for this experiment? So let's make a list of our materials. So materials. What are our materials? Well, we're gonna need a hot plate that has a magnetic stir. Right? We're gonna need a magnetic stir bar. What else are we gonna need? We're gonna need a bottle of water. We're gonna need our water bottle, our trusty water bottle. We're gonna need a 10 milliliter graduated cylinder. What else? We're gonna need a ring stand. A thermometer. We're gonna use a burette clamp. We're also gonna need a styrofoam cup. That's going to be our coffee cup. We're going to need some cardboard. We're going to need some 3% hydrogen peroxide. And we're going to need some 0.5 molar iron 3 nitrate. I do believe that's, sometimes I use rubber bands. That's to hold the lid on. So let's see. That looks like a good materials list. Make sure you write that down in your lab notebooks. Those are the materials. Again, a magnetic hot plate, magnetic stir bar, water bottle, 10 milliliter graduated cylinder, ring stand, thermometer, burette clamp, styrofoam cup, cardboard, 3% hydrogen peroxide, 0.5 molar, iron 3 nitrate, and rubber bands. I do believe paper towels. We don't need to include that, but yeah, we'll definitely probably need some paper towels. That is our starting list for materials. That's kind of fun. Let's kind of look at that. All right, now that's a big list of materials. What are we going to do with that? So let's look. Let's talk about setup first. We're going to set this up. We're going to set up. How's our setup going to look? Well, let's look here. Over here, this is going to be our magnetic hot plate, a magnetic stirring hot plate. That's how we'll abbreviate that. Here's a knob that we can turn so we can make it stir. On top of that, we're going to have our coffee cup. We're going to have our coffee cup, and we're going to put a little bit of that hydrogen peroxide in there. There it is. Also, inside that hot coffee cup, we're going to have a little tiny magnetic stir bar, so that when we turn this spins, makes a little tornado. I'll show you that. It's pretty cool. There's a little metal plate under the ceramic part of the hot plate, and this is hooked to here, and it makes this metal plate spin, and since this is magnetic, this stir bar spins with it. Pretty nifty design. I have got my ring stand attached to the back of my hot plate here, so here's my ring stand. right? And that ring stand is just, I'm going to use that burette clamp. So here's that burette clamp, right? A little twangy thing here, and my thermometer is going to sit right in here. And that's going to be my thermometer. Right? I'm going to put that through a hole in some cardboard. So here's cardboard. So what do we have? We have our styrofoam cup. Oops. Our thermometer. Our ring stand. Our burette clamp. Our cardboard, our stirring, our magnetic stir bar, So that's pretty much everything sitting right in there. That's kind of our apparatus. That's our setup. The rest of the stuff is going to be used for either dispensing or is a reagent itself. So the water bottle, we'll use that to give our graduated cylinder a couple rinses. The 3% hydrogen peroxide is in a bottle, and the iron. It looks like we're probably ready to talk about some procedure sets that we're going to kind of follow here. And so we'll kind of look at those next. So here's our setup. Make sure you copy that down into your lab notebooks just in case you possibly need it. I'm going to clear those drawings, and we're going to just continue with our procedure set. Well, our procedures. Step 1, setup. Well, we're definitely going to do that. I'm going to do that here in a second, and I'm going to show you guys my setup, and when it's done, we're going to just kind of plug right along through. Step 2. We're going to take 50 milliliters of our 3% hydrogen peroxide and place in coffee cup. 3. We're going to stick in, bar. Stick in that magnetic stirring bar. 4. And stir low power. 4. What are we going to do for it? 4, we are going to record temperature for about 4 minutes. And we're going to take one reading every minute. Nice. That's what we're going to do. It'll go quicker for you. It's going to be slow for me. But that's going to be that first part. Make sure you copy these down really quick. I need more room. So we are going to record the temperature for every minute for 4 minutes. So really it takes 5 minutes because the first one, and then a minute. So about 5 minutes a time. So I will kind of fast forward through that. I'm going to erase this. We're going to move on with step 5. Step 5. At that 5 minute mark, we're going to add 10 milliliters of our 0.5 molar iron 3 nitrate solution. We're going to be quick about this and get that cardboard lid back on real fast. We don't want any heat exchange, any heat escape. I'll talk about some little fudge numbers here towards the end of this that we have to add in, factor in some heat loss due to the calorimeter, and so we'll talk about a calorimeter constant, that kind of fun stuff. It shouldn't be too bad. Okay, number 6. Let's look at number 6. What are we going to do? Well, now we're going to, again, record temperature change every minute for approximately 15 to 20 minutes. We will see, we're going to wait for high temp, then wait longer for it to start cooling back down. Cooling I talk way faster than I write. Cooling back down. Cool. Then we'll have all of our data. That'll be nice because after we have all of our data, 7, we're going to graph our temperatures, temperature versus time, and we're going to look for our actual delta T, our change in temperature. Because if you remember, we're still going to be using this equation. Q equals Cp times M times delta T, where Cp is going to be our specific heat capacity of our solution, mass is going to be the mass of our solution, and delta T is going to be our change in temperature so that we can quantify and calculate this heat energy. That's our big goal, our heat energy. So we'll walk through some calculations probably towards the end of this. Well, that's our apparatus setup, that's our procedure set, those are our materials lists, kind of our goal. I'm going to get set up and we're going to start rocking and rolling so that I can get this produced out there for you guys to kind of look at and follow, answer some questions about. See you here in just a second. Okay, I figured why not let you watch me here really quick. I just tried to cut a piece of cardboard that fits that, and look at, yeah, nope, yeah. Measure twice, cut once, Hibbert, so yeah. So I'm going to do this again, so my cutting skills are not up to par. I need one just a little bit bigger. Alright, so these, I would be in so much trouble if I was caught using these scissors for this kind of shenanigans, but you gotta make do with what you got at the home. Okay, so there we go, that's a much better lid. That one's actually gonna fit. Yes. Rubber band to hold the lid down. If you look down in here, I already have my magnetic stir bar. See, I don't know if you can see it on that camera. That camera's good too. And so I've got that set up. I've got my burette clamp. If you look up here, I've got my burette clamp. It's ready to go. It's going to be holding our thermometer down into our solution. Through that cardboard lid. Beautiful, right? And then again, what do I have down here? I have my reagents. I've got my graduated cylinder, a spare Teflon stir stick, and another coffee cup, and my reagents and my water bottle. That's kind of what we're looking at currently. Yay! And so I'm all set up. I'm going to get some stuff ready to go, like my hot plate plugged in, because that would have been a good thing to do. And then I got to get my goggles on, because this is not about protecting my forehead. I understand. It keeps the wrinkles away, but it's about protecting the eyeballs. So my PPE needs to be like on my face and not anywhere else. Bam! Look at, they're on my face. Just it happened. It was great. Everything's plugged in, good to go. Well, let's see if we can get some noise with the stir plate, stir bar, because sometimes doesn't work. I think you can hear it. It's been in my classroom before. You've seen that. You've heard that before. Let's look and see what it's doing. There it is. Oh, whoa, which way? There it is. Isn't that amazing? I can slow it down. I can speed it up. I can slow it down. Alright, so that's going to stir our reaction as our reaction takes place. Beautiful. Okay, so we are all set up. We're ready to go. I wonder if that would be a cool view. Oh yeah, we'll do that. We'll do that as we look. I will make sure you guys get to see some of the stuff that I see, but we also want to see some temperature change. Whoa! Alright. We got that set up. We're ready to rock and roll. I am going to measure out the 3% hydrogen peroxide, add it to the reaction vessel, and get my pen and paper, and we're going to start taking some data. Alright, I put in 10 mils of the hydrogen peroxide. Let's do another about 10 mils. This is not the best way to do this, folks, but again, we do what we can where we're at. There's another 10 mils. How many mils did I say? Remind me again. Oh, 50. So we are, what, 2/5 of the way done. About 40%, just a little bit more. There's 30. Remember, we're trying to read right at the bottom of that meniscus. And it's not really easy to do this way. I wish I had brought a pipette home. 40. Last one, folks. And 50. So if we can see where, oh, that's 9 mils, yeah. And 50 mils. We got 50 mils of our 3% hydrogen peroxide sitting in that vessel. So if we look in there, it's stirring around. Now, I've got to lower this thermometer down into that and start taking my temperature reading. So what do I need out? Well, golly be goodness, I need this piece of paper right here. And I need to title something, probably time. I have my trusty watch on, so I'm going to get my stopwatch ready. That's not it. And let's find it. There it is. Eyes. There it is. And again, so I'm going to drop this down into my solution. Ooh, cardboard. Shoot-a-mundo. Forgot about that piece. Alright, so we don't want that hole too big, we want it just right. We'll put that about right there. And I don't even think we're going to need that rubber band, but we might. Up a little bit first so I can get that right in there, because we don't want that to touch our magnetic stir bar. Oops, like that. Hey, look at that. Now, I've got a terrible view of the thermometer. You guys probably have a much better view of the thermometer. So we are going to start our 1 minute now, and I will take a temperature reading in approximately 1 minute. Right now, it looks like it's... We started at about 18 degrees C. I'm not even going to cut that part out. You see that experiments, that's what they do. They go crazy sometimes. We're going to say just in that first place, about 18 C. That's not even data we're really going to need. Well, yeah, we should probably take it. We're almost up to our first minute. We're at our first minute. So we're going to call it 18.0. 18.0 degrees Celsius. That's at minute mark 1. That's at the 1 minute mark. Okay, that was fast. We're almost at the 2 minute mark. We are now at the 2 minute mark, and it is 18 degrees Celsius. Make sure you're writing this down. 2 minute mark, 18.0 degrees Celsius. 18.0 degrees Celsius. 2 minutes. 2 minutes. Few more to do. While I took the time last minute, I filled this up with our iron 3 nitrate solution. Look at that. Nice and kind of orangish. So we'll be looking at some color change possibly during this here little experiment as well. 2 minutes, 26 seconds. Let's make the last 30 seconds go real fast. It's like I'm a time traveler. We got just a couple seconds left. We're at 3 minutes now. And lo and behold, we are at 18.0 degrees Celsius. I know, we're just getting a baseline, folks. That's kind of what we have to do. Make sure we know exactly that initial temperature so that we can calculate that temperature change effectively. Okay, 1 more minute of this, and I add in fun stuff. Okay, we're coming up on that time, that 4 minute mark where we have to add stuff in, so we're going to try to look at all of this fun stuff at the same time. This might be kind of hazardous. So let's see if I can, oh, no, that's not going to work. But we're at the 4 minute mark, we're at 18 degrees Celsius, 18 degrees Celsius, and so we're going to crank this up. Sorry folks, it is kind of difficult to try to show you what's happening and get superbly accurate measurements, but I did want you to see this because it's kind of fun. So again, we're going to catalyze this reaction. So here we go, we're going to drop this. Here's our iron 3 nitrate. Wow, look at that color change. It's like soda pop. It's even going to start bubbling out some oxygen gas, but we want to put that back in there. We're going to get that thermometer back in there, and we need to take temperature readings from now until forever. If you've done your math correctly, you should know. There's the bubbles happening. Nice bubbles. Right? If you've done the math correctly, we now have 60 milliliters of solution. We're coming up on 5 minutes. 5 minutes. 5 minutes. 5 minutes. And we are at 19.0 degrees at 5 minutes. 19.0 degrees at 5 minutes. So again, we've got now about 60 milliliters of solution in there. So I'm going to make another column of known stuff. So I know I now have 60 milliliters of hydrogen peroxide and 60 milliliters of the iron 3 nitrate. Neat thing is it's mostly water, so we can look at our mass. If we remember the density of water is 1 gram per milliliter. So 1 gram per milliliter, we have 60 milliliters, so I'm assuming we probably have about 60 grams. 60 grams. 60 grams. Why is that important? Well, if you remember that equation, Q equals Cp m delta T, the m stands for mass. So now we have our m, we have our m, we have our m. We know it's water, and our m is 60 grams. That also gives us our specific heat capacity. I'll talk about it here in a second because we need another temperature reading because I talked for a minute. And we are now at 23.5 degrees. 23.5 degrees Celsius. Woohoo! Gosh, it's warming up in here. 23.5 degrees. Specific heat capacity. We talked about that. You did a calculation. Specific heat capacity of water is 4.184 joules per gram degree Celsius. Holy mackerel, we have some information. Really all we need is our delta T, and we can calculate the heat. And that's our main goal today. That's our main goal. I have to talk to you about an enthalpy of reaction. I'm going to lecture about that on Friday. We're going to use this information as part of that lecture so that I can teach you how to calculate the molar enthalpy. Some of you are going to be able to do it. Some of you are going to take this and run. You're going to know that you're going to be like, it's hydrogen peroxide. It's 3% by mass of that 50 milliliters or 50 grams, this many grams was hydrogen peroxide. I can calculate the molarity. Holy moly, I know what I'm doing. We're at 7 minutes. Here we go. 7 minutes, and we are at 28.0 degrees. 7 minutes, 28.0 degrees Celsius. Wonderful, beautiful, love it. Okay, and we're just going to keep rocking and rolling through this. Well, I'm not going to try to make you stay for every minute, but just want to make sure that you can kind of think your way through that molar enthalpy problem. Okay, we are at 8 minutes, and we are at 30.2 degrees. We're at 30.2 degrees Celsius. That's 30.2. We're at 8 minutes. Look at that temperature. That temperature is going up. It's cool. Or it's hot. That's something to think about during this break. Whew! Time's going fast for you guys. 9 minutes. 9 minutes now. We're at 9 minutes, and we are at 31.5 degrees. 31.5. 31.5 degrees. Seems our temperature is going up slower now, but it's still going up. Cool. Or hot. Ugh. I thought I argued about that last break. 10-minute mark. 10-minute mark. We're at 31.5. 31.5 degrees Celsius. So it looks as if to me we're going to start leveling off. Now, past this, we want 4 or 5 measurements past where we see that max temp, because we're going to have to do something with the line. And I've talked to you guys about this word before. We are going to extrapolate data. So we're going to graph this here in a second. We're going to graph it, we're going to get some data, we're going to extrapolate, we're going to do a calculation, and we'll be done with this heat part, and then we'll continue the molar enthalpy part during lecture on Friday on how to get through that portion. So we're at 10 minutes, 50 seconds. I might as well just keep talking for the 11 minute. 11 minute, 11 minute, 11 minute, and we are at 31.0. 31.0 degrees. 31.0 degrees. 31.0. That's what we're at currently. We're at 12 minutes right now. 30.5. 30.5. 12 minutes, 30.5 degrees Celsius. We're still going to take a couple more measurements. Let's go up to 15. We got to go to 15 minutes for sure. 15 minutes sounds good. And we're at 13 minutes and we're still collecting data. Yeah. Oh, wait, yeah, no singing. 30. It looks like 30 exact on the nose. So what are we going to call it, folks? 30.0. So 13 is 30.0 degrees Celsius. A couple more minutes of this. Like I said, folks, I will help with some of the molar enthalpy stuff here, but we should be able to do Q equals CP delta T. You have CP, you have M. We're going to graph to find delta T, and then I may just make this part of a quiz and not give you the answer and have you calculate it for me. Okay, fine. I'll do it again. I'll help you through it again, and then you'll just take a pretty gnarly quiz. It'll be all right. 14 minutes, and we're at 29.5. 29 point. I see a trend in losing heat energy. 29.5. Interesting. 29.5. One more, and I think we'll probably be safe with that. That will give us 5 measurements past the max that we recorded, so we can extrapolate and find the actual max temp that it got to. All right, we are coming up on the 15-minute mark, and what are we going to have? And yeah, we could have probably predicted it from our trend. It looks like about 29 degrees Celsius, and it's because it's cold down here in my dungeon, and so with that level, the scissors, I'm sitting on the scissors, ouch. And it's probably why it's losing heat a little bit faster than I would say it usually does in a lab setting. Instead of 23 degrees Celsius, we're at 18 down here, so it's getting a little bit chilly. That is the end of the so-called experiment. We have gathered our data, right? And so we should have a piece of paper, some kind of tablature that looks like this, where we start with that time 0 at 18 degrees Celsius, and we just trickle on up to our max and drop back down slowly over time. I've got my 60 mils of solution at 1 gram per milliliter, which gives me 60 grams of material that changed temperature. That temperature change equates to a specific heat capacity of 4.184 joules per gram degree Celsius. So now we can start setting up some math after we've got to extrapolate some data. So let's look at some data extrapolation. Oh wait, no, I wanted to show you this first, because remember what that looked like when we put that in there, when we dropped that iron 3 nitrate into that solution, and it started doing its thing. If we look, we now have a different color of solution. It's no longer dark. It's still kind of orangey, right? It was the high molarity iron nitrate. So yeah, it kind of turned from soda pop into orange juice. Still not anything at all anybody should ever drink. Oh my gosh, that's just, my kids, they like to ask that all the time. Can I drink it? No, you can't. All right, extrapolate the data. All right, there we did. I just did a quick little Excel spreadsheet thingy thing here where I stuck in my time, and I stuck in my values for temperature. I did a nice little scatter plot, and I got temperature versus time here. So we can see we had this flat line, 18 degrees Celsius, and all of a sudden, wham, and then it starts decreasing. So what I mean by extrapolate is we're going to take this line of data here. See how this is a trend line? We're going to take that and we are going to extend that up. And we're going to say that it probably actually maxed out at about 35. If you can imagine a line, this being a line, it would hit possibly that 35 mark, which means we're just going to call it 35.0. It's going to give us the data that we need to do this. We'll see how close we are. There's an actual number, and again, I have to talk to you about the calorimetry constant. And so we've gone from 18 degrees Celsius, our T1, our temperature 1, let's see if I can do this. Our temp initial was 18.0, and our temp final was, what are we saying? We're going to say about 35.0. That's pretty close. We can do a linear regression just on those little pieces here, but I want to shorten this video. It's already getting really long, and I apologize for that. And so really what we need to do is we need to figure out what the difference between these two numbers are. And you can probably see it right now. The difference between those two numbers, if I subtract them, is a total of 17.0 degrees Celsius. So that's going to be our delta T. So that's really super slick because now we have all of our information. We have our mass, we have our specific heat capacity, and we have our change in temperature. And so again, we're just going to go through the process of calculating that Q to figure out the total amount of heat given off from this experiment. All right, got my trusty whiteboard. So let's look at what we currently have as far as information. So we know we have the mass of the solution that we used. The mass was 60 grams. That's important information. We know the CP, that specific heat capacity of water, is 4.184 joules per gram degree Celsius. So we have that information as well. Right, and what else do we know? We know that our delta T was 35.0 minus 18.0, final minus initial, and that delta gives us a 17.0 degrees Celsius delta T. So now we remember that Q equals CP M delta T. So we just have to throw in our numbers. We have 4.184 joules per gram degree Celsius times 60 grams times 17 degrees Celsius. Well, again, when we look at this basic unit analysis, grams are going to cancel, Celsius is going to cancel. It's going to give us a unit in joules, which is appropriate. That's appropriate for that. Let me see if I can find my handy dandy calculator. Look, it's the Hibbs calc. The Hibbs calc. You guys remember those. You miss those. Best calculators on the planet Earth. Let's look. 4.184 times 60 times 17. The first time I plug it in gives me 4.268 times 10 to the third joules. 4.268 times 10 to the third joules. That's not bad. I'm going to plug those numbers again because I've seen you guys use these calculators and I know that fingers get in the way. 4.184 times 60 times 17. The second time gives me the same number. So I'm going to call that good. So that is my joules. That is my joules that I liberated from the reaction. Now, we still have to talk about one other thing. All right, so now we have this value. We have this value of there it is. Let's clear all these. 4.268 times 10 to the third joules. Now, again, we had this container here, and the water got warmer, so our system gave off energy. If you were to lose money, would that money be positive or negative? Well, of course it'd be negative. Energy is the same way. Energy exiting the system is a negative value. So this is actually Q. The Q of the solution is equal to negative 4.268 times 10 to the third joules. And we have calculated our Q, which is really nice, but that's just the Q of our solution. We really need Q total. Well, Q total is going to be our Q of solution plus the Q of the calorimeter, that calorimetry constant bugger. And now I just calculated that here a second ago, and I came up with roughly about 5 joules per degree Celsius for our calorimetry Q. So therefore, with that constant, so we have 5 joules per gram degree Celsius, and our equation for that is actually, it's a negative, let's look, a negative calorimetry constant times delta T, and so we'd have negative 5 times 17 gives us a negative 85. So we have negative 4.268 times 10 to the third plus a negative 85 joules. Well, cool. We can do that math. We can take 4.268 plus 0.085,
and we can calculate our actual answer. So our Q total, calculating, ends up being 4.353 joules, and that's negative. Well, that's pretty cool. That's good information. That is how many joules of energy were produced by the decomposition of some amount of H2O2. Well, again, we use 3%. I'm wondering if any of you have the ability to figure out molar enthalpy before I talk to you about it and teach it to you on Friday. Now, as far as a little quiz or assessment so far over calorimetry, you'll just get this part. AP kids, if you are sneaking in and looking at this, I expect you to be able to do this part. See if you can come up with an answer for the molar enthalpy of the breakdown of that amount of 3% hydrogen peroxide if it gave off negative 4.353 joules. Oh, kilojoules. Oh my goodness. Kilojoules. Could I go back in time? I apologize. When I moved this, and I just kept writing it down as joules. Wow. Bad, Hibbert. Erase your brains. Go back. I'm going to have to redo the whole video. You're going to have to watch 2 of these. No, that's not what's happening. We are going to be finished with it there. I'm sorry I made a mistake. All right, well, we're going to wrap up lab today. My class is getting a little bit out of hand back here. Matthew, Kenai, quiet down. Behave yourselves, everybody. Man, I miss y'all. It was fun doing lab with you. Make sure you understand the procedure sets for calorimetry. Make sure you kind of understand the goal there. Again, we're going to use this data. If you have any questions, get online, get a hold of me. Not asking you to do too much today except for watch this video and answer some questions later on this evening. Possibly, probably not. We'll probably just kind of leave it for tomorrow and I'll give you something to do as far as just like 3 or 4 questions. Other than that, adios amigos. I can take these off now and look, hey, look it. We know what that is. Very few of us that have those. It's the mark of smart. They protect your eyeballs and they bless you with the mark of smart. Mine's pretty good today. I've seen some better ones on you guys. Miss you bunches. Keep doing chem. Rock on. I will see you on the flip side.